All right, hello everybody. Can everybody hear me? Can I get a thumbs up from somebody? Great, 2 thumbs up, that's almost a quorum. So on Wednesday of this week, Prof. Talvati is going to be giving a guest lecture on discussing her research area, which is model-based reinforcement learning. So please attend and give her a warm welcome. As well, the grading I wanted to let you know is up to date, except, let's see, there were a few late submittal PA 6s. 6 is the last one, yes. So there are a few of those. And if that is you, if you turned in late, if you haven't got a grade on yours yet, please go ahead and email me to let me know that it's in and when it was in. In addition, if you can take a look at Sakai and just make sure that you have all the scores that you think that you should, so I'm not missing anything for you. So I believe I have all the programming assignments, quizzes, and homeworks done, except of course for today's homework. Any questions before we get started? So we're in kind of the home stretch of the class. Next week will be the end of lectures. The final exam, I was originally going to be handing out in class on the last day of class, but since we don't have class that day, we'll be doing like we did with midterm 2, and I will be providing you a PDF. It actually won't be on the last day of class. I believe it's mid-week through the next week, so it's on the schedule. And then you have until Friday of finals week to turn that in, whether you're a senior or not a senior. Okay, and I imagine you all know, but just to make sure you don't, so you all have an option for taking this class, pass. I don't know whether it's pass, no credit. Part of it depends on what college you're from, but you all do have that option. And so I'm going to assume you're going to go with letter grades unless I hear otherwise, but you can let me know if you want to be changing that. All right, let's go ahead and get started. So I wanted to talk in more detail about stochastic gradient descent. I realized I kind of left off what I think is a very useful diagram. And so let's go ahead and take a look at that. So this useful diagram is this diagram, which some may say is not actually all that useful, but it will become useful as we fill it in. All right, so let's look at this. So what have we got actually coming in that we're trying to learn? Varun, what is it we're actually trying to learn with our stochastic gradient descent? Oh, and that's right. Let me bring up chat because, so we're trying to use an approximate value function that could be used to generate a policy. That's right. So what is the data that we're using to train this approximate value function? S to G. All right, so we've got an S that's coming in, and then we have got a value for it, right, which changes over time. But as far as the reinforcement learning, we think there's really 2 parts to this kind of. There's a reinforcement learning part of this, and there's a learning an approximate value of which function. The reinforcement learning part, we have a state function. We have, this value function for our state that we have a actual value that we want to set it to, right? Which is part of the way from the current value of that state to G of t, okay? And so we can think of that as sort of our V pi of S. That's what we're trying to learn. Now our V pi itself is an approximation because of the reinforcement learning algorithm, right? So the fact that we are only eventually getting to that V sub pi. But at any point in time, we have a current estimate of our V sub pi. And so this is kind of our input. Hold on just a second. I've got a whining dog. So she, I think, wants to be in my lap. She's 45 pounds, not really a lap dog, but in any case. So our input is our S. And then what we've got for our V sub pi is, let's say, our actual value, right? So this is our unapproximated value, okay? So that's our inputs. And then what we're trying to produce is our approximate value, which we're going to be calling V hat. Okay? If we talked about this in a sort of a traditional machine learning framework, we might call this our Y. That's our output. Okay. So we've got our input S. We are using feature extraction. At least right now. Okay, that's a fairly common machine learning technique where we take our input and then we extract from it useful features that we think will be useful for a machine learning model. When we get to looking at neural networks, we're not going to use that feature extraction because we go ahead and let the neural network figure out what features it thinks are important or not. So the feature extraction we're going to be using is some X of S, where we're going to extract particular interesting things from the state. So this output, X of S, then is going to get fed into our function, that is the approximate value function. So this is our V hat function. So it's a V hat, and it takes Nelson. What parameters does V hat take?
It takes the weights W.
Sorry, I can't hear you. Just a second. Go ahead.
It takes the weights W and the state values.
Right. So it takes the state features, right? So we've actually pre-processed that state in some way. And so it takes X of S as a second parameter. So that's coming in from the top. And then from the left, it'll take our weights. Okay. And Nelson, in the particular example we were looking at in class on Wednesday, what was that function? So how were the weights and the X's utilized?
Like, do you mean when we did the linear example?
Yep.
It's just a vector product.
Yeah, just a vector product. So we take our weights and multiply it by our X. Okay. And then what comes out is our approximate value, right? I'm going to just call that V hat by itself, right? So that's what is our current estimate of the V of S, given our incoming S and given our current set of weights. And that can be close to V sub pi, and it could be very far from V sub pi, right? And we want to get some idea of whether we're close or far. Because if we're close, we might want to tweak W a little bit, but if we're far, we want to make a major modification to the weights. So Jacob, in the bottom here, so what is this box at the bottom, which has V hat coming in and also has our V sub pi coming in?
That'll be our loss function.
This would be our loss function. Okay. When you are designing stochastic gradient descent algorithms, right, when you are doing this machine learning, you actually get to choose what is your function going to be. You get to choose what your loss function is going to be, and then we'll also see you get to choose the remaining box. But our loss function, what loss function, Jacob, were we using on Wednesday?
We're using mean squared error.
Yes, we were using mean squared error. So we were basically saying the loss, which from the book we called VE, often it's just called, let's say, L, is the difference between our target and our actual. So it's basically the difference between V hat and V sub pi. And I'm ignoring some parameters there, right? And squaring that. Okay, so that tells us close or far. So what comes out of here then is our loss. And we need to evaluate that loss. And this box here, Julius. I don't know that you necessarily know what this box is. If you took the neural nets class, go ahead. Do you know what that is?
So it's the thing that comes out of the loss function.
Hold on just a second. Let me increase my volume. Say that again.
Can you hear me?
Yep, I can hear you.
So it's a output of the loss function that goes and updates the weights, right?
Yep,
So,
it's the thing that updates the weights. I'm going to call that the optimizer.
optimizer.
Okay, so this optimizer's job is to update W based on the loss, right? And so what we saw is we were going to update W. We were going to take, I'm going to throw in a 1/2 here for the moment. We'll talk about that later. 1/2 alpha times a difference. And what we really want to look at is the gradient of the loss. I'm going to just write it as loss here. Okay. That is, we want to figure out for each component of W, if we change W, right, or what is its partial derivative? Kind of what is its slope at the current value of W and S. And so some of those components will have higher slope, some of those components will have more shallow slope, and we want to go in the opposite direction of the slope so that we are reducing the loss. And we're going to go in the direction as specified by the slope, and we're going to use the magnitude of the slope to tell us how far to go. Why do we have this alpha, Shannon?
Anytime we have an alpha, it's because the algorithm is stochastic and you don't want to move it like all the way in the direction of whatever the target is.
Yeah, I think that's part of the reason, and it doesn't. We don't require stochasticity in order to need an alpha here. A bigger reason is, I think that the slope, right, gives us, let's say we're 5/1, the slope is 5. Why should we necessarily be moving 5 units, right? The slope just says basically that if you move an epsilon amount, that your, in the x direction, that your y direction is going to move a 5 epsilon amount. And so why would moving 5 units necessarily make sense, right? So this just controls, it really is controlling, if we think of it, how fast we're going down our hill, right? If we go too far, we might just cruise right past the minimum and up over the top. And if we go too little, we might just making these tiny steps that take forever. I'll give you an example. So let's look at this in the two-dimensional case, right? So we've got here something like that. And if we are, I don't know, let's say we're here, which is a pretty high slope. And let's just kind of put some units on here. So if we moved by, I don't know, 5 of those tick marks, where would that be taking us to? So we're here at this red area. And if we moved 5 units to the left, 5 of these axes units to the left, we'd be sort of off over at 0. So we'd be way past the global minimum. According to sort of this graph, we want to be moving when we're here in units of maybe, I don't know, half a grid unit, you know, rather than 5, let's say. If, on the other hand, instead of being there, or let's say here, up in the top right, if we moved a tiny fraction of a grid unit, first, it'd take us forever to be moving, and second, we could easily get stuck here at the bottom, right, once we get down there. Because as we get down there, the local neighborhood around us has a 0 slope. Okay. Now, even if we use a small, what's called learning rate, which is that alpha, even with a small learning rate, we can still get out of local minima like this using the stochasticity, right? So if we look at the loss for all of our, let's call them training examples, so all of our S comma V pi sub S's, it may be that we're stuck at this local minimum, right? That our gradient is 0, in this case, in the one direction that we have. But if we take any one training example, it may have non-zero gradient. So that one training example may be enough to kind of kick us out of this local minimum. Okay. Does that concept make sense? Why it is that we get a value of doing gradient descent. So if we look at gradient descent, at, let's say, one extreme, we could have all of our inputs, that is, all of our training examples, all together, okay? The nice thing about this is if we had them all together and computed the average gradient, that would be exactly the direction we want to move for this whole set of inputs. The problem is severalfold. So one problem, we have lots of computation if we have a lot of input before we even take one step towards adjusting our weights. Okay, so it's not unlike when we talk about, let's say, TD0 versus Monte Carlo, where in TD0 we can update a state immediately, whereas in Monte Carlo we have to wait till the end of an episode in order to do updates. So in the, let me back up a second. Instead of TD0, let's look at TDN. So we have a long N versus a short N. In the short N, we get to start making updates to our estimates very quickly. Whereas in the TDN, we have to wait until we take in steps. Or maybe another example would be the dynamic programming example, where do we want to go ahead and make one pass through everything or just update one state? So in any case, we have lots of computation. That's a problem. An advantage is our gradient is, let's call it sort of exactly right. On the other hand, we can look at a single input. If we look at a single input, then it's quicker to calculate. We're updating W sooner, right? It's probably, if we start out with random weights, it's probably enough to look at a single input to tell us, hey, we really should be going in this direction. There's a lot of change we need to make to W to make it reasonable. And you can do that without having to look at all your inputs. And then there's in between, and that is to use mini batches. That is to say, let's grab a, pardon me, a handful of inputs and calculate our gradient, our average gradient, and use that average gradient. Questions? Okay.
I have a question.
Go ahead.
So in terms of the learning rate, when do we want a high learning rate and when do we want a low?
So you would want a high learning rate often at the beginning of your training. So you can make sort of quick progress and then reduce the learning rate. So you can try and go down into a valley of a minimum. As well, it may be that you want different learning rates for different components of W. So you might have components of W that tend to be, let's say the direction of your update stays the same time after time after time after time. And so there, you might as well go ahead and increase your learning rate. Whereas if you have a W where you are changing the direction of your update, so first you're decrementing it, then you're incrementing it, then you're decrementing, then you're incrementing it, that's probably a better candidate for having a lower learning rate. Now, you wouldn't want to be setting up by hand learning rates or learning rate schedules for every one of your weights. So there are different optimizers that will go ahead and adjust learning rates automatically. This is kind of the very simplest optimizer, but there are 5, 10 you might use. And when you are solving a problem with stochastic gradient descent, that's one of the choices you have, is which optimizer am I going to be using? And often optimizers have parameters associated with them, hyperparameters. So not only which optimizer, but then which hyperparameters associated with it. Alpha here is one such hyperparameter. That you would need to be setting your loss function and then the structure of your approximation function. What, is it a linear function? Is it a neural net? If it's a neural net, how deep is it? How many units? All these sorts of things. All those are hyperparameters, decisions that you have to make in trying to solve your problem. And very often, you have to try different things in order to make it work.
Makes sense.
Prof. Rhodes?
Yeah, Mazda.
So I have a quick question in terms of the overall applications of this sort of framework for reinforcement learning problems, particularly in the case where we don't really know our true values. So I can imagine if we have DP, maybe this could help. But otherwise, would we instead want our loss to be something like relative to the negation of our total reward?
Well, so we are trying to approximate a value function, right? That's our goal of what we're trying to do here. Is we still have our reinforcement learning framework. The difference is instead of having when we update the value for a given state, so either a V or a Q or a given state action, we are only approximately updating it instead of absolutely updating it. So we definitely have an additional source of error here, right? Because not only do we have the errors of doing reinforcement learning of the fact that we don't currently have the actual V sub pi or Q sub pi we're only sort of on the way. Now we also have an additional error of the fact that that is also not accurately what we saved last time. It's only approximation. This all can work though. Basically what happens is your approximate value function, you're going to be giving it some values for v sub pi, and they're going to be changing over time, of course, because as your reinforcement learning algorithm works, it's going to be changing that value. You're going to have to be updating your approximate value function in that same way, and it is going to be seeing this sort of non-stationary v sub pi. But over time, part of what we do in training approximate value function, the stochastic gradient descent, is we will provide the same input-output pair more than once. And so commonly what will happen is we will calculate what a current v sub pi is. We will save it. We'll feed that into our neural network along with a whole bunch of other saved s and v sub pi's. And then over time, we'll sort of drop those out of our bucket of things to be trained. And so the old values will go away and we'll get new values in, which will be more updated or more current values for v sub pi. So our approximate value function will change over time. Our w is changing over time. One way to think of it is really that our graph itself here is changing. So it might start out, let's say, as blue, but then, you know, turn into, I don't know, something like this as our v sub pi updates. Does that answer your question?
Yeah, I think so. So just to clarify one part,
Sure.
when you were mentioning the computation of those input-output pairs, to determine those v sub pi's, are we just using like any of the different strategies that we've learned up to this
TD,
point?
for example, yeah.
Got you.
We'd
Cool.
be commonly, but it would. So yeah, that is an important point, is that this is, so let's look a second. Right, let's say we have our TD algorithm, right, where we are going through and we are, you know, Q, let's use, I don't know what we want to use. And we have an alpha here, and it's going to be a different alpha. Okay, so this is our reinforcement learning alpha as opposed to our function approximation alpha. But in any case, right, this is going to be our reward plus, let's say, our max over all A of Q of S prime, comma, A prime, right? All right, so there's two parts here where we'd use our function approximation. We'd use our function approximation here, and so we would approximate Q with our V hat. Yeah, it really should be Q hat, right? If we're gonna be approximating Qs. Okay. So here is where we are actually estimating. We are saying, given a particular state and action pair, what does our function approximation say those values are? Okay. Then we'll go ahead and get a new value. So we now have our new value of Q of S comma A. And now we're going to say our new training example is S. I wish I'd been using V here. But we're using, so here we'd be, our input would be the pair S comma A, and the target value, or Y, would be our new Q of SA that we calculated. Okay. So another way to look at this is, right, this would be the input, and this would be the Y. And that would be now a single training example. And then this is all, of course, embodied in a larger TD loop, right? And this is just a single step in here where we're using function approximation. We're using function approximation to both get an old value function that we've approximated, and then also to, in some sense, set the value. Our setting the value, though, is basically creating a training example. And then once we've created that training example, we will use it with stochastic gradient descent. We might use it once. We might use it many times. We might choose to use it immediately. That is, generate a new value for Q and then go run a single stochastic gradient descent. Generate, run a single one. Alternately, what we might do is create a whole batch of them. We might create 50,000 of them, let's say, and then store those in a replay buffer, and then feed those into stochastic gradient descent using mini batches one or more times, so that would get W to tend to converge to some value. And then we would go back into temporal difference learning again, into the reinforcement learning, use our new W, create a bunch of new values, and so on. Does that help with explaining kind of how those go together with the reinforcement learning?
Yeah, so I guess my main confusion was like, if we're already going to be doing this TD or whatever we need to do to approximate VPi, why go through all the work of the neural net? But I think I'm seeing that the advantage is actually learning what that value function is, so we can apply it to, you know, inputs that we haven't seen before as well.
Well, there's twofold, right? One is, so let's assume for a moment that our problem is too large to do tabular, okay? If our problem is too large to do tabular, then the question is, how is it we're going to be able to know what our Q of S prime A prime R, right? We need that somewhere. It's not in a table. Where is it? It's in our approximation. So it is, in some sense, embodied in our W, right? W contains all the information we need to know in order to approximate what Q of S prime comma A prime is.
Well, okay, that's I understand. That's very cool. So the bootstrapping now also uses this approximate function that we're learning, and it's like doubly bootstrapped.
It's doubly bootstrapped. In some sense, what we're doing is we come up with, so you know how normally what do we set our Qs to when we're bootstrapping?
Just whatever it was the last time we calculated it.
Yeah, this is induction. We're going back. We have a base case. When we start from the very beginning, what do we set our Qs to?
I recall sometimes there's 0, sometimes random, sometimes maybe like slightly more than 0.
Yeah, it's in fact, if we look at the algorithms, we can set them to whatever we want. Often we will set them to 0. The fact that we can set them to whatever we want is really key, because when we start this process with our approximation function, our W is initialized randomly, in fact. And so that is going to impose random Q hats, right? Mm-hmm. Or V hats, depending on whether we're looking at state action or just action pairs. And so that's okay. We're allowed to have random initial Q values, right? That is, the TD will work in the face of that, because we have to initialize into something. And so initializing W is going to be really initializing what those Q hats are indirectly.
Cool, thanks.
Sure thing. All right. So what I'd like to do is go through and look at doing homework, whatever this last homework was that homework 10? Using this framework. Oops. All right. So let's go through and just kind of fill in some parts of this. So Justin, what's this here? So our top line to fill in. What does it represent? And what's its actual value?
Sorry, just pulling up homework 10 again.
Oh yeah, so that's a good point. Yeah, for the values, I can help you out if you need here.
Oh, sure.
But what does this represent?
That's the input, right? So
The input, which in our case, this is the input that we're taking to approximate, right? So we've got some function, you know, f of something. So in our case, what's the something? What kind of a thing is the something? State, action, value?
It would be a state value approximation.
Okay, so it is a state value approximation, but what we're trying to do is approximate. Right? So we have v hat of s equals, you know, some value.
Mm-hmm.
If we look at this formula, what is this input representing? The output of the function, the input of the function?
That represents the output of the function.
Actually, the right-hand side is going to be the output. So
yeah, that's what I meant. Sorry.
So the left-hand side is the input, which is basically s. It's our state.
Okay.
Okay. And if you happen to have the homework open.
I do.
Okay, what is this state?
2.
2, right? So this was a t equals 2. Okay, and while we're at it, what's the output?
The output was
the correct output, right? So the correct output is v sub pi of s. Mm-hmm. So presumably we did a step of reinforcement learning. Could have been temporal difference, could have been Monte Carlo, could have been something else, but we came up with what our estimate of v sub pi is. And what is it in the homework?
7.
7. Okay. Make sense so far?
Mm-hmm.
Okay. Let's see. So Garrett, as I remember, we didn't actually have feature extraction in this homework.
No, we were provided with the v of pi function, or
yeah, we could just say x of s equals s if we wanted, you know, but maybe we'll just get rid of that, right? We didn't have it. So we still have a state coming in here. And then what did our v hat look like?
The function was w2 times s squared plus w1 times s plus w0.
Yeah, I think you are right. w2s squared plus w1s plus w0. Okay, so it's not a linear function, right?
No.
It's quadratic. Okay, so it's slightly different formulation from the linear functions that we looked at on Wednesday. All right, what do you need in order to actually calculate this value?
S?
You've got S. Actually, what is S?
Oh, you need the weight vectors at W2,
yeah,
W1, and W0.
And what was the weight vector?
In order 0, 1, 2, I think it's 1, 3, 3.
Oh, I was going about to write 0, 1, 2. So 1, 3,
sorry.
3. Yeah, 1, 3, 3. All right. And while we're here, what is then v hat equal?
The target or the output?
The output of this
estimate.
v hat function. Yeah, this estimate, the v hat.
19, I believe.
19. So let's just try w2 is 3 times 4 plus 3 times 2 plus 1 equals, yes, 12, 12, 18, 19. Yes. So we've got 19 coming out here. So, thanks, Garrett. Mark. So this next box that has our two inputs of 19 and 7, what does this box represent?
The state loss.
So this is our state loss, right? The overall loss is just the average state loss. We're just dealing with the one here, right? One of those. And so what is the state loss?
It's the absolute value of the difference between the output and the estimate squared, which is negative 12 squared.
So I understand that absolute, but I don't think the absolute was in there, right? Because if we're going to square it, we don't really care whether it's absolute or not, right?
Sure.
So equals 12 squared equals 144. Okay, is that a big loss?
Pretty big.
And I'd say, who knows? What is the range? This might be an extremely tight, I don't know. But we could probably do better. Okay. Dave, the next box. So we got 144 coming out of here.
Yeah, so now this is where we have to update the weights.
Yep, so this is our optimizer box, right?
Yep.
Let's look, instead of looking at the gradient, which is a vector, let's just look at the derivative for W sub 0, right? That first element of W. So if we say W0 equals W0 minus, and we're minusing because?
Because we're trying to go the opposite direction of the slope.
Yeah, exactly. Opposite direction of the slope. I'm going to throw 1/2 in here. We'll get back to that in a moment. 1/2 alpha times the partial derivative of the loss with respect to W0, right?
Mm-hmm.
Any questions on that, anyone? All right, so that's going to equal, well, so what's the partial derivative of loss with respect to W0? I'm going to write over here. So the partial derivative of the loss with respect to W0, if we just use the chain rule, is the partial derivative of the loss with respect to the partial derivative of V hat times the partial derivative of V hat with respect to W0. People agree with that? So the loss with respect to V hat, let's just remind ourselves. So the loss is equal to V hat minus V pi squared. Again, I'm leaving out the parameters there. So the loss with respect to V hat is just 2 times V hat minus V sub pi. Do you agree, Dave?
Yeah, that looks right.
Okay, and the derivative of V hat with respect to W0?
With respect to W0, so V hat is expressed by W2 S squared by that, yep.
Yep, and so if we take the derivative of that with respect to W0, that says all the other W's are constants, right?
Yeah. So we're just left with a 1.
Left with a 1, agreed. So therefore, we're just at 2 times the difference, right?
Mm-hmm.
So this is equal to 1 minus 1/2 times alpha times 2 times V hat minus V sub pi, which, and it is not an accident that these cancel out, equals, oops, equals 1 minus alpha times 19 minus 7, right? Equals 1 minus 12.12, because alpha was 0.01, equals 0.88. Now, some of you probably got a different answer. Someone raised their hand who got a different answer. No one? All right. Yes, Nelson, go ahead.
Oh, I think I just did it wrong.
Oh, okay. Well, if you did, that's fine. The one thing about well, okay. So one thing about it is there's a 1/2 that's kind of hanging around somewhere. Often what really happens, and I didn't specify it this way, but often what happens is that the loss is actually 1/2 times v hat minus v pi squared, right? If you just look at the mean squared error, you'll see that often they throw in a 1/2 there when you get into gradient descent. And the reason they throw a 1/2 in there is exactly so that when you take the derivative, the 1/2 goes away. And so you don't have a 2 hanging around, okay? So many of you probably also would not have a 1/2 here. And so therefore, we would have 1 minus 0.24, I guess, which is 0.76. Either one of those is fine. Okay, so I could just as well imagine this without the 1/2. Okay, and certainly in the grading, either one was fine. So if, Sean, you have a question?
Yeah, yeah. I'm a little confused. How come might have missed this? How come we're only looking at W0? I thought we took the gradient.
We took the gradient. It's just because the gradient isn't necessarily a very common thing for people to do, and it's really straightforward if you don't know what gradients are, but you just know about partial derivatives to do each one individually. Gotcha. So let's go ahead and do it all at once. All right.
Can I ask a quick question?
Yeah.
I thought alpha was 0.1, so wouldn't it be 1.2, not 0.12?
I thought alpha was 0.01. Let's check. I'm just bringing up the homework on my screen, which you can't see. The learning rate is 0.01, according to the homework. So, if you did 0.1, and I know at least someone did, then, I just made a note saying that was the wrong learning rate. All right, let's go ahead and look at this in terms of doing the gradient. So if we're doing the gradient, so if we look at del, basically, of the loss, this is going to be an array which will be the derivative of the loss with respect to W0 and then W1 and then W2, right? So we can look at this sort of as loss, W0, loss, W1, and loss, W2. we've already figured out the first entry here, right? The loss with respect to W0, we said was 0.12 or 0.24. I'm going to just use the case without the 2. The loss with respect to W1, so I guess here we really want to know what the partial derivative of v hat with respect to W1 is. And Sean, what's that?
Could you repeat the question again?
What's the partial derivative of v hat with respect to W1?
That would be, let me just find the, okay, that would be 1 plus S plus 1.
So hold on a second. How are you getting a 1?
Oh, sorry. It would just be S.
S. Oh, great, right. Because all the other W's are constant.
Right.
And so we just have S. And while you're at it, the derivative with respect to W2?
W2S.
So let's talk about that again.
Sorry, S squared.
Yes. Yeah, we're not going to take derivatives of everything, just the one variable.
Right.
All right. So if we come back, let's see. Actually, so if we look at this, erase this for a moment. It's not what I wanted. I want to erase. So we know the derivative loss with respect to the v hat is v hat minus v sub pi, right? And with W0, we multiply the derivative of v hat with respect to V0. So that's the first. And then the second is v hat minus v sub pi times S. And the third is v hat minus v sub pi times S squared. Right? So given we know the value of S and v hat and v prime, that again is, what is it, 12. 12 times 2 is 24, and 48, yeah? And so now, if we say W equals W minus alpha times del loss, we can say that's really equal. And the del loss, just because of the fact that W is a column vector, will transpose the gradient there. So this is, what was it, 133 minus 0.01 times 12, 24, 48. All right, and it's that matrix form that actually computations are going to normally be done, either in NumPy or if you're doing neural nets, more commonly be done on a GPU, allowing the GPU to do this matrix computation very quickly. Any question on the problem?
I have one quick question.
Go ahead, Mastan.
I've sometimes seen like in order to allow for a bias to also be like accounted into our linear term, is it just kind of like implicit that our first feature is just always 1?
Let's talk about that. So here we go. Here's our slide. Why do we have a 1 here? So commonly what will happen is you'll want some bias, right? You'll want an ability to say, let's say, even if all the other features are 0, that you still have some non-zero value. And so an easy way to do that is to have one of the features just always be a constant 1. So here, for example, if you're looking at S, right? So if we back up a second, why would linear not be sufficient? So let's say, for example, let's say we have a state which is composed of 2 values, S1, S2. Okay. First off, have we ever seen a state composed of multiple values? Anyone in any of our, let's say, program assignments or anything else? How about 21, right? Blackjack. What was our state representation? Kaki, do you remember?
I don't quite remember.
So, okay, so let's say we're playing blackjack. What would we want to know?
If we're over 21.
Well, if we're over 21, yes, it's over. That's certainly true. What else?
If we are on 21.
Okay, if we're on 21, what else?
If we're under, whether to get another card or stay.
Well, that is our decision we need to make, right? So that's going to be an action, which is whether to stay or to hit. But what are we looking at? Look at the board. We're playing just with a dealer and with us. What's the important information?
The number that we have right now.
Okay, so we want, the total we have right now. That's one piece of information. And what else?
The number that the dealer has.
Yep,
right now.
so the dealer's up card. And I'm going to just ignore aces and the fact that those can be. But that's an example where this is roughly what you might want for blackjack, right? What's the dealer's up card? And how much do you have so far? And that is enough to tell you whether you want to hit or not, right? So that kind of fits in this S1, S2 idea. If we have a linear model, that is our V hat is equal to WT times X of S, is there any way that we can model sort of interactions between our 2 components of our state? I mean, sometimes we might want to do that, right? We want to say, what happens if both things are occurring, or if neither is occurring, or if one is occurring, not the other, or the other occurring is not the first, and so on. And so what we can do is we can get some nonlinearity by having our features incorporate nonlinearity, right? So S1 and S2 are sort of are elements that are pulled out of the state that will then go into our linear model. And this all stays linear. But we could also have a feature that is like S1 times S2. So that would allow us to capture some of the interactions between S1 and S2. Or we can actually do, squaring S1 squared. I intended for this to be S1 squared times S2 squared. I apologize. So this allows us to effectively get a polynomial model, right? By having basically polynomials in our feature extraction and then feeding that into a linear model. And as you pointed out, Mazda, this 1 here allows us to have just a bias, right? Because basically this 1 is going to be a 1 no matter, right? If we look at a given X of S, any x of s is always going to have a 1 here, and then some other values. And so whatever the first weight is going to be some bias such that if the rest of the wx's add up to 0, this will give us some non-zero value. Or another way to think of it is if we have, this is our v hat, that I don't know, looks like this, right? So this is s, and this is v hat of s. If we wanted to just translate this up or down, then we would just adjust the first weight, w sub 1, because it's always multiplied by 1. Did it address your question, Muslim?
Yeah, that's good. Thank you.
Okay. We need not have polynomials for our feature extraction. There are lots of different features that one can use. If I look at, let's say, non-neural nets and neural nets, so to separate the in non-neural nets, we usually will have S going into some feature extraction that gives us our x of s. And that then goes into our model, where I don't mean by model my reinforcement learning model, I mean by model my function approximation model. So it'll come into my function approximation and our W will come into there. Okay. In neural nets, it's real common to do what's called end-to-end learning. End-to-end learning, where the idea is you don't try and extract features you think will be useful. Instead, you feed S into this big neural network. Okay. And in the neural network, the beginning part learns to do feature extraction. Okay. So rather than you a priori trying to figure out what you think would be good features, you say, I trust that the neural network will learn whatever features it thinks are useful. So that it will first take S as input, and then it will modify it and extract things and combine them together in order to get useful features that'll then go down the later parts of the neural net. We'll talk briefly about neural nets on Monday. Mostly we're just going to view it as a black box, though, and a black box that you could feed the state into. So if we had, let's say, a chess, what we might feed in as our state would be a chessboard. Now, how would we represent the chessboard? We might represent the chessboard as 8x8 matrix with, I guess, a number at each entry. Representing the piece that's there. That's one possibility. Neural networks often find it easier to work if you have made a simpler representation. So instead, we might have sort of a 8x8 saying where the white pawns are. Another 8x8 for the white rooks. So just have a bunch of these 8x8s so that it's less densely coded than it is here. All right, so here's what I want to talk about next. I want to look at one particular reinforcement learning problem that we talked about but haven't seen particularly, and that's the cart pull problem. Okay. So I'm going to first just show it to you, show you a video. So let's see. That's not what I want. So it'll be just a second. Okay, so this is the cart pull problem in physical real world. Okay, so what we have is, you could ignore this for a moment. Can everyone see that video? Yeah, we got a thumbs up. Okay, so what we've got is a pole that's mounted, that can go left or right, mounted on this cart, and the cart can move left or right. So the cart moves left and right and is attempting to balance this pole. So it doesn't work well to begin with. And it starts in the middle and it doesn't do well. I'm going to skip ahead. And oh, it did it for about 3 seconds. And then it whacked into the side. It's not doing bad. And knocks it over. He cheats a little bit sometimes by just giving it a little tap to make sure it stays up. But over time, it begins to learn to actually balance it. Okay. That's the goal of the cart pull problem. The cart pull problem, can you see the animated cart pull here? Thumbs up or thumbs no? Thumbs up? Okay, I just wasn't sure exactly how this is being shown. So this is the cart pull problem in an animated world. And here it's doing a pretty good job of balancing it. Ideally, it balances it in the middle of the track that the cart is on. So let's look at that cart pull problem and see what's involved with it. So our input is a cart position. So this is from left to right. A velocity as to how fast the cart is going. A pole angle, which is how far from zero is the pole. And then how fast is the pole moving. So this is the speed of the pole. And so we get this four tuple, which is the state. So cart pause, cart velocity, pole angle, pole velocity. Is this a problem that can be solved without reinforcement learning? Yes, it is. But it's a nice and fairly simple problem to solve with reinforcement learning. The possible actions are just move left, move right. Okay. And then we've got a reward for every step taken. So basically, you're being rewarded for how long it manages to keep it balanced. Okay. And the episode is over if either it is tilting over too much, so the pole is tilted, or the cart hit the edge, or you got more than 500, because basically we get bored after a while. And if you've done 500 steps, then we pretty much understand that you've mastered this problem. So why, Sean, why would we need to use an approximation or state approximation for this?
Because an angle, it's hard to measure, like discrete measurements, perhaps.
Well, here's our values that we're getting in, right? We're getting our angle.
Oh, okay.
Yeah. So it's a real number.
Um,
These are reals and these are reals.
Then the state space is really big.
How big is the state space?
Well, I suppose you'd have a different state for each cart position, and then
how many different cart positions are there?
4.8.
4.9. No, so these are real numbers. So I might be at 239, or I might be 238.
Oh.
9999995.
Sorry.
Right?
I meant 40. Oh, so then it could be really, really big then if you have.
How big? How about uncountably big, actually? I mean,
yeah.
The fact that we're using floating point numbers on an actual computer means that we do have some finite number of these, but practically, right, we're in roughly, r to the fourth, which is infinite. So we don't have any, we have conceptually an infinite number of values for each one of these components of the state.
Right.
And therefore tabular isn't going to work, right?
Mm-hmm.
So we have an infinite number of states. So that's why we need approximation. Now, what you might have done, Sean, and this is reasonable, is you were talking, I think, about how many cart positions do you think you need? Maybe we don't really need to distinguish 2.39 from 2.3899999995.
Mm-hmm.
So we could discretize these, right, or bucketize them. We could say that the cart position, we're going to keep to, let's say, 2 decimal places. The velocity, we could keep to, the velocity is a little more difficult because we would not need to know what maximum velocity we have. But the angles we could also discretize. So we could do this bucketing and just assume that if we had, let's say, this would be kind of a 4-dimensional bucket where we are rounding the cart position, the pole angle, and the other 2 elements. And then our assumption is that, the assumption is that states in the bucket can be treated the same way. Okay, but an alternate approach to dealing with the approximation, because this is certainly one kind of an approximation, an alternate is to stochastic gradient descent. And that deals with approximation. If we were going to use a linear model, again, let's go on to Nick. So if we're going to do a linear model, Nick, how big is W going to be?
So are we assuming that we're just using those 4 features?
It's an excellent question. I like it. So how many features do you want?
Well, we probably, if we want to make it the simplest model, let's just have 5 features where you have 1 for each of the inputs and then 1 for a bias.
So we could have 1 and then S1, S2, S3, and S4, right?
Mm-hmm.
We will probably end up with a problem with that, but I think it's a good way to start, right? But I think we would find that we would fail here. And part of the reason we would fail is that what we do is going to be very dependent on not only, let's say, on the pole angle, but also the velocity. And so the combination of those 2 might turn out to be important.
Mm-hmm.
how could we represent that?
So you could have it be where you actually are multiplying the two together.
Yeah, we could add an S3, S4
Yeah.
interaction there if we wanted. Okay. All right, our last programming assignment, I haven't fully decided, but I believe is going to be a cart pull problem. And I do want to show you, just to begin with, that there is a toolkit for reinforcement learning from OpenAI. So it's called the GYM, and it's a toolkit for developing and comparing reinforcement learning algorithms. So people see how well they do on various OpenAI GYM problems, or also add new problems. So an example of things that can be in there are Atari games. So if you want to play Space Invaders or various other things, then you can use OpenAI GYM for that. Some of you may have also seen like walking four-legged creatures. Those are also a component of OpenAI GYM, although they require a physics engine that is licensed along with it to work. But that is how you can try and use reinforcement learning to teach a four-legged, animalish thing to actually walk. But as you can see, this is the code. So we just import the GYM. We say what problem we are dealing with. We get an observation, and then we go through and render. This is to make our movie, to make a frame of our movie. And then there's an action space in the environment. This is the part where we decide what to do. Okay? The simplest thing is a equal probable, which is what this is. Which, by the way, does not last long in dealing with cart pull. And then, and this may look familiar, you take a step in the environment with an action, and you get back an observation where, as I remember the observation, I believe is the state, the immediate reward, whether this is over, and some other additional info. Okay. So the part that's of interest here, of course, is specifying your action. And so what we'll look at doing for the program assignment is using stochastic gradient descent to basically decide on what your action is. Questions on this?
So I had a question about, so earlier you used a Q learning type of update. Is it always Q learning, or can you do like some kind of n step update? Because I could think of like sometimes there wouldn't be that many rewards for like a long time, and I feel like that Q update wouldn't really work that well necessarily.
You could do whatever you wanted. You would still be needing to learn Q values rather than V values, because you need the Q values to determine what to do, right? To tell you which action to take. But you could use, I just picked Q learning out of a hat. It could have been anything. So we could use n-step TD. We could use just any of the reinforcement learning techniques that we have looked at. The model-free ones. In this case, as we look, we don't have our model in the GYM environment. Okay. I will say again that Wednesday's lecture is going to be a guest lecture by Prof. Talvati. She's going to be talking about model-based RL. I hope to see you all there. I will be there as well. And quiz today on Gradescope. If there are any questions, I will hang around for office hours in this Zoom meeting. Okay. If I'm gone for 5 minutes, just come back to the meeting. And maybe I'm just trying to save the video. Otherwise, I will see you on Wednesday.